in both rooms, probably computer science. Last speaker for today is Rob, who will give us his final lecture on entanglement.
Okay. So in about an hour, you're going to face an important decision. You can listen to the rest of my lecture, or you can head to the beach. So, Orange said, I'll see you.
The bus will wait. The bus will wait.
In any event, once more into the breach with quantum entanglement. So I introduced the idea of holographic complexity last day, and I want to continue on the complexity theme. Last day we saw that, or what I talked about were these two new gravitational observables, and they're interesting in their own right, but the suggestion is that they satisfy various properties that are in line with our expectations about complexity. But we'd really like to understand what this thing is, or what these things are that we're looking at. What is this holographic complexity? And that really requires working harder to try and match what we're doing in the bulk with something in the boundary theory. And so that would require that we really understand what complexity means when we come to talk about quantum field theory. And so that's really what the topic today is. Whereas I brought you to the cutting edge of research, now we're stepping over that edge into the abyss. And I'm going to describe a few tentative steps in that direction that some folks have been working with. And I know there are other people. Shira is also working with her group on similar ideas. But before we get started, because complexity is a new idea, I just wanted to remind you about what the basic rules of the game are. We're going to measure how hard it is to prepare a certain state. In particular, we have in mind in holographic complexity a state in the boundary theory. Now I'm going to be talking about a particular quantum field theory, and I want to know how hard it is to build a state. So we're going to start with a simple reference state. And if I'm talking about a string of qubits, it might be a string all qubits, all spins pointing down. Then I want to build a unitary operator that takes that simple reference state, rotates me through the Hilbert space, and puts me on the desired state. But the rule is that I'm only allowed to build that unitary out of a certain set of Lego blocks, these simple universal gates. And I'm allowed to put them together in some kind of quantum circuit that performs this particular operation. I also mentioned that in general, the quantum information theorists talk about there being a tolerance because I might not quite get to where I want to get, but I might get close enough. In any event, the idea is that I do this operation, I build the most efficient circuit possible, and then I count the number of gates. And that gives me a number, and that's what we call the complexity. A theme that ran through the lecture last day was the idea that I made a whole bunch of choices, the reference state, the gates I'm using, the tolerance, and those are going to affect a precise number that comes out of my calculation. But I hope that what I tried to convey as well is that, you know, if we do this calculation many, many different times in different contexts, it still contains some interesting information when I compare all of the numbers. There are questions that we can ask, which, independent of our choices, the complexity is going to give us some interesting physics answer about the physics. And so today the idea is, how do we apply these ideas to quantum field theory? Or the question is, how do we apply these ideas to quantum field theory? But perhaps I should just pause and ask if there are any rule or questions about these general rules. If not, we'll charge ahead. I want a quantum field theory. What's the simplest thing I can think about? Well, I think about a scalar field theory. So here I've written down some Hamiltonian for a scalar field theory in d space-time dimensions. One of the things you note is down on the end there's a potentially complicated potential for our scalar field. and that's a little bit intimidating. So for our first steps, I want to make it even simpler than that, and I'm just going to look at a free scalar field theory. I'm just going to reduce the potential down to a simple master. Now, many of you, or some of you, may be asking, what am I going to learn from a free scalar field theory about holographic complexity, where I'm talking about strongly coupled large N CFTs. And so to keep you engaged with the lecture, I'll let you know, or I'll remind you first about this connection between a certain set of quantum circuits and the complexity equals volume idea. And then what I'm going to tell you, or additionally, is that in fact there's a continuum version of the Mira network, which was built specifically, or well, the test case in which it was first applied, or one of the test cases, is to build the ground state of a free scalar field. And so one of my hopes, my earnest hopes in starting this, is that I was going to recover, or I was going to see signs of this hyperbolic geometry in our calculations of complexity. Unfortunately, a spoiler alert is that that remains a question on the last transparency. Where is that hyperbolic geometry? But in any event, let's just see. So here's my free scalar field theory. The first thing I'm going to do is I'm going to regulate. And so to regulate, I'm going to put it on a lattice. But what have I really done? Then I've reduced the problem to an infinite set of coupled harmonic oscillators. Now this is quantum mechanics, and it starts to sound like a doable problem. But that infinite is still an intimidating factor. And so what I'm going to do is simplify the problem even more. And I'm going to start by thinking about two coupled harmonic oscillators. That same problem that we had as a warm-up for the entanglement entropy. And so what are we supposed to do with two coupled harmonic oscillators? Well, we're supposed to find the normal modes. Then I reduce the problem to two independent harmonic oscillators. I can do things like write down the ground state wave function, or if I insist on working in my original coordinates, the positions of the two masses, I get again some Gaussian, but it has this interesting factor where I can see that the two masses are now entangled because of that cross curve. And so, well, I'll pause there and say, well, isn't that an interesting state? It's a particularly simple, perhaps, as a first step, target state. And so our aim is going to be, can we build this state? But we're supposed to build that state from a simple reference state. And so what am I going to use as a simple reference state? Well, again, what I'm going to use is a Gaussian, but I'm going to use a Gaussian where that cross term disappears, and so there is no entanglement between the two masses. And I'm also going to introduce a new frequency, omega naught, that's going to be just some independent parameter. We're going to decide, or we're going to talk about how to choose it at the very end of the lecture. But for now, it's just some parameter that characterizes our reference state. And so it characterizes our model for calculating the complexity. So we've got a target state, we have a reference state. The next thing that we needed were unitaries, or gates, to build our circuit, which was going to take us from one to the other. And so, well, it's a quantum mechanics problem, and so the natural operators that we're given are the x's and the p's. And those aren't unitaries, but it's easy to build unitaries using those. And so I'll start, well, with this one, which is a rather simple or a silly unitary, because those x naughts and the p, or the x naught and the p naught are not one of our operators. They're just c numbers. They're just placeholders. And so all this does is, if I multiply my state by this gate, is it adds a small phase. And it adds a small phase because I've introduced the epsilon as well. And so the epsilon is going to be a key that appears in all of the gates because I want my gate to make a very small change to the state. And it's only by applying many, many, many gates that I want to be able to get from, well, a finite distance away from my reference state. And so that's what makes this well, these gates give a small action. So that's a rather trivial gate. Here are some others that we're familiar with. I can stick a PI up there, and then it's in the exponent, then it becomes a translation operator. What I'm doing with a PI is I'm shifting, the gate shifts xi by a small c number, epsilon times x naught. Similarly, when I've got an xi, in some sense I'm shifting the momentum by an epsilon p naught. Since I'm working in position space, all I'm really doing is I'm multiplying by a small plane wave component, or I'm adding that, or multiplying that into the wave function. Things get more interesting when I put two of my x's, or an x and a p up in the exponent, and there's two different possibilities. The first is that the indices are different, and then what I'm doing in this with this particular gate is I'm shifting xj, but I'm shifting it by the operator xi, well, with this small coefficient. And so what that's doing is it's entangling the two masses. And so I call that an entangling gate. The other possibility is the indices match, so there's no sum here, this has just got an I on it. And so what I'm doing is I'm shifting xi by a small x amount proportional to xi, but that really turns out to be a rescaling. And so hidden in the sign here, it says scaling, and I'll refer to that as a scaling here. And you can continue this game, and you can build more and more complex gates. I can stick two x's, two p's, three x's, two x's and a p. But I know that, in fact, this set of gates is enough to carry out the operation that I want. And so I'm going to stop here. In a more complete or in a more complicated theory, I can expect that I need these extra gates for more complicated operations, but they're not going to play a role for the particular problem that I picked out as our practice problem. So given given our states, our reference state, our target state, our gates, what do? Well, we start to put together circuits, and the circuit's supposed to take me from the reference state to the target state. And so what does that circuit there do? Well, it operates with this scaling gate the number of times, well, alpha 1 times. And so what that's doing is it's scaling up the x, or the x1 in particular. And so I know that I have to go from an exponent omega naught to an exponent omega 1, and so that'll let me, with the appropriate number of that particular gate, that'll scale up that part of the wave function. But then I also need that cross term, and so I act with this entangling gate some number of times, and then I'm going to have to also match the exponent in x2, and so I'll need to do some scaling in x2. And so it's an exercise, I won't go through the details, but you can figure out what those exponents are that I need for that circuit to accomplish the desired operation. And then you add up the exponents, or you actually add up the absolute value of the exponent. And that's what you might call the complexity, but this is really only one sample circuit. It's not the optimal circuit, and so I'm going to call it the circuit depth. I'm going to steal some words and use them inappropriately, but I'll call this the circuit depth just to make sure that we don't confuse it with the optimal circuit, or the length of the optimal circuit. In any event, you can see there that, well, basically there's a factor of 1 over epsilon, and then there's a bunch of other factors that involve the various parameters that appeared in our two states, or the target state and the reference state. And so this is a particular possibility. As an aside, I mentioned this tolerance at the beginning, and so here when I do this problem, it's natural to think that those alphas are just real numbers, but if I really thought of them as integers, then I might not actually get to the desired target state, but I could get very close to it. And so you'd have to define some measure of success. So here's a possibility. It's not the only possibility, but you might take the overlap of your final state with the target state, and it could be very close to 1, but not quite equal to 1. And so you can do a couple of things. One is you can just try and minimize the overlap. using integer exponents, or you could set some tolerance, and the tolerance would be proportional to this epsilon that appears in the problem. But again, if I use real numbers or real exponents there, that wouldn't be a problem, and essentially in the rest of the lecture, the numbers up there will be real numbers, and so this idea of a tolerance just disappears from the lecture henceforth. But before it disappears, I'll pause again, and I'll ask if there are any questions about that. Okay, if not, we'll carry on. But this again is one sample, one possibility, and I can certainly put those gates together in many, many different ways and carry out the same transformation from the reference state to the target state. Question is, how do we find the optimal way to carry out that operation? And the way I'm going to do that is I'm going to follow an approach, or I'm going to steal some ideas from Mike Nielsen, who talked about circuit complexity in a slightly different problem, and he in turn stole ideas from the theory of Hamiltonian control, which is a topic of interest to quantum information and condensed matter folks. So how do we proceed there? Well, first of all, just to compare, what he was thinking about was I had a simple state of n qubits, and he wanted to do a unit, or he wanted to find a circuit that would take him to some specified state of those qubits. So he's doing a little bit different problem. It was more the problem that I was describing when I described the rules of complexity. But his first intuition, or his first idea is that rather than working with these discrete gates and discrete components, we should think about smooth functions and a smooth space, because it's easier to optimize on that by varying, well, by functional variation. And so what I'm going to do is I'm going to think of my circuit as follows. The q's have disappeared, but you can see that the operators, those o's that appeared in the exponent, are appearing up there in this exponential. And the epsilon has also disappeared, but you can think of that as the ds that appears in this integral. And you can think of those y's then as I'm moving along this line of ds from 0 to 1, and the y's are, well, they're functions, but they're telling me when I'm turning on a gate and when I'm turning it off. And so you can think of those as some kind of on-off functions for each one of these operators here. So those are roughly like the alphas that appeared as the exponents of our gates. And so again, the idea is that that circuit is going to perform the desired transformation. There's also this p here. This is like a path-ordered exponential because the first operator acts on the state on the left, and then at ds equals, the delta ds, the next operator acts on that and that and that. And so I'm building up the circuit moving left to, or right to left. And that's what that path ordering indicates. Mike also said that, rather than just thinking about the total circuit, what counts is how you put the gates together, or how you put these operators together. And so you really want to think about the trajectory through the space of unitaries, or rather than just the final unitary. And so what he suggests then is doing not an integral from 0 to 1, but doing an integral from 0 to s, and then I have a family of unitaries that characterize a certain trajectory in this space. And the unitary, so I have a u of s now. U of s starts at 1, and it ends with the final unitary, the final operator that performs the desired transformation. In this perspective, you can also think of these y's as velocities along this trajectory. And, well, there's a very specific way in which you think of it as a velocity. and it's just this formula here. I take a derivative, that brings out a derivative with respect to s of this expression, that brings out the last operator, which for him was that matrix M. Then I multiply by u inverse. I'm multiplying on the right, that gets rid of the rest of the exponential. And then there's some basis of these, for him, matrices. And so he takes a trace to identify the various components of yi. And so in that, in the sense that I'm taking this derivative, I can see it as a velocity along this trajectory of unitary. So that's a lot of words, so I should pause. Oh, there's a question.
Yeah, I wanted to ask, this construction sequence is reversible. Is it not?
In that I can take u inverse and apply it to the target state and get,
To start
Sure.
from the more complex state and get to the less complex state, and then if I do same, then how do you determine which is more complex?
so yeah, okay, no, but it's certainly true that it's a unitary operator. By definition, that means there's an inverse, so I can put the u inverse on the other side of the equation. But the question was, what defined a simple reference state? And so there, I used some kind of, I made an arbitrary choice at some level, but I used some kind of physical intuition that what made my reference state simple was the idea that there was no entanglement between different positions. So later on, when we think of it, the lattice again, we want to think that different points on the lattice are completely unentangled. And that's really the guiding principle or the definition of simplicity for me. It's a proposal to what simplicity is. You may have another choice, and you get a different set of numbers, and you could compare numbers and see what kind of physics they're talking. Are there other questions?
Where does S live? Like what?
Where did S?
Where does S live? Is it the XY site?
No, S is an artificial parameter. It's just, I have, you can think again, if I go back here, what I have is a chain of gates, and rather than multiplying by a particular exponent, you can just think that here's my reference state, and I'm going to act with one gate at a time. And in some sense, S is just a parameter that runs along. And I've divided my chain into, n steps, and so each step I'm labeling with a different S as I go along. But then we've sort of combined it all in this continuum expression. It became a path integral. It's not a path integral, but a path ordered integral of, well, that exponential. Other questions? Well, sure, velocity, we did that. So we've got this interesting idea that now our unitary, or our circuit is some kind of trajectory through the space of unitaries. It's going from a definite starting point to a definite ending point. And so Mike had the intuition that I can think of this as the motion of a particle, and that I'm minimizing means I'm minimizing a cost function, but I can think of it as the old problem, or the familiar problem in physics of minimizing an action. What's the action that we're using? Well, it was summing up, absolute values of all of these exponents alpha, but that's really counting how many times I turned on and off a circuit, so it's summing up the yi. So that would be the analog here. And again, a small aside is that here when I'm adding things up, there's a ds, and so that's like sticking an epsilon in the sum. And so before I had a circuit depth that went like 1 over epsilon. Afterwards, you're going to see I'm going to give you complexities or circuit depths that are finite numbers. And the reason is essentially that I'm sticking this epsilon into the sum. So I kind of did a redefinition where there's a slight change there, but that's a small aside. The key idea, or what Mike was on to say, is that if you think about this problem, this is a geodesic in something called Finsler geometry, which is very interesting, but I don't have enough time to tell you what Finsler geometry is, and so I put a reference to Wikipedia there. And you can go and explore the interesting possibilities. Instead, what I'm going to do is I'm going to change the cost function. And I'm going to write it like this. So it's the square root of the velocity squared. And this is a particular example of a Finsler geometry, it turns out. But in going to this particular choice, it's something that we're all, well, hopefully we're going to recognize. It's just the usual geodesic equation in a Riemannian geometry. And so I can use a lot of intuition from classical mechanics or perhaps general relativity in solving this particular problem for geodesics in some unusual space. And we'll figure out what that space is. Another comment on something that I may or may not get to is that you may not want, what that was doing was it was counting each different gate with the same weight, or each different step or possible direction with the same weight. You might not want to do that. You might want to weight certain gates more than others. You might think that certain gates are more costly than other gates. And so rather than having a delta ij there, you might have something, some more general metric or matrix that connects the velocity. Okay, so here we've got our problem. We've got some set of trajectories in circuit space. We've got an action or a cost function, which is just a geodesic equation. The one thing that I have to do, or remains, is really define what those yi's are. And Mike gave me an expression, but that was an expression that really referred to matrices and not operators. It actually isn't that difficult to work directly with the operators, but at the time we were doing this, I thought that it was easier just to work with matrices, and so what I'm going to do next is I'm going to turn our problem into a matrix problem. And so what we're doing is really going from one Gaussian state to another Gaussian state, or wave function. And so rather than thinking of the wave function itself, I'm just going to think of the quadratic form that characterizes the Gaussian. And so rather than writing down that ground state wave function, I'm just going to write down this matrix that appears up there in the exponent. And our target state, or our reference state, was just a simple diagonal form or matrix, and we're aiming for this more complicated matrix. Yeah?
Maybe I missed something here, but I thought it was important for the discussion that you had a notion of simple gates, and that you were building your circuit out of simple gates.
Right.
But when you're doing geodesics on the unitary group, it seems like you're imagining you could use any complicated non-unitary group, like just exponentiate to get the unitary group.
And so there are, that comes down to this question about the Gij. Rather than excluding directions, what the suggestion is to take advantage of this technology. We'll just, at the end of the day, you'll penalize certain directions as being very costly. In his language, those were gates that, or transformations that involve many, many qubits. Those were penalized as opposed to, well, his favorites were just the ones that manipulated 2 qubits at a time. And so there's some notion of k-local. It's not quite, it's not the same as local in space, which actually will become a guiding principle later on for us. But there is a notion. But rather than just trying to cut the geometry down, what we're going to do is try and penalize those directions so that we're sort of guide along particular favorable directions. I'm not sure if that made you happy or not. But that's the philosophy that he takes, yeah.
You expect the choice of the norm in your action,
The choice of the,
the norm in
oh, the norm, yeah.
to affect your conclusion regarding.
It will, and I'm going to talk about that a little bit at the end, or what some of the different effects are with different choices. Okay, so now I've identified an interesting matrix problem. You can actually transport or translate your gates into gates that act on these quadratic forms, and they actually act with some kind of similarity transformation here, where the generators now are just simple matrices where there's a 1 in one component and a bunch of zeros, like that example there. But you can also see now that the group that we're working with those generators, is the group GL2, or general linear transformation of two variables. And so now I've just got, my generators are all matrices, I can just plug them into this formula and everything carries on amazingly well. One comment is that, ultimately, again, the goal is to think about a lattice or a chain of these oscillators. And I've set up the notation in a way that is easy to do that. Rather than running over a sum of 1 and 2, you just let the sum run over the entire lattice of oscillators. Another comment is that there's a mismatch in the parameters. GL2 is a 4-dimensional space. There are 4 generators. But we're looking at symmetric, the space that we're working on are these symmetric quadratic forms, and those are all, that's only a 3-dimensional space. And so there's a mismatch there. But that's okay. That's just telling us that, in fact, there's not one solution to this problem. There are going to be many geodesics that will accomplish the desired transformation, or many U's that are geodesic that carry out the desired transformation. And I'm just going to minimize, I'm just going to look at all of those geodesics, and I'm going to find the one that has the minimal length, according to our cost function. But that's just a warning for something that we're going to see later. So the first thing is, what is the geometry that we're really talking about? Well, it's this group. We have to get to grips with GL2, which you can think of as SL2 and an extra scale transformation. But let's focus on SL2. An interesting way to write an SL2 matrix is with parameterize it as I did there, because then the constraint that you're imposing is that the determinant of that matrix should be equal to 1, which reduces to this equation, which for readers of the HEP-TH bulletin board is familiar, because that's just that's an equation that defines AES3. And so there's an interesting hyperbolic geometry that suddenly jumps out at us. But we wanted to study GL2, we should use that to give us some intuition for coordinates, and so we picked some coordinates here that are standard coordinates. Rho would be a radius to AES3, theta is an angle, and tau would be like the time direction. But we actually wanted to look at GL2, and so we don't want to restrict the determinant to be 1. We want it to be any positive value, and so we'll parameterize it with an exponential like that. And so that throws in an extra coordinate y in our expressions here. But what happens when I stick those coordinates into that matrix U? I get some expression like this. Then I'm supposed to build a metric using this technology that I talked about, and you end up with a metric that looks like that. Now, unfortunately, if you stare at that metric for a long time, you will not see AES3, because it isn't AES3. And in fact, that's a good thing because this is actually the embedding surface for a Lorentzian ADS3. And we wouldn't want our space to have negative norm directions because that would say that in fact, well, there are directions that have no cost in all directions and directions that have a negative cost if I go in other particular directions. And it's really because I chose this delta ij that I got some other metric that ensured that all the directions were positive or that I had a Euclidean metric. I can get that metric over there, but that involves replacing the delta ij by some kind of Minkowski space metric. And what it amounts to is that's actually the natural geometry, or the group invariant geometry, which means it's the left-right invariant geometry. But what I built here is something that's only right invariant, and it's not left invariant. Because, well, if it matters, you can see from this expression here, you can multiply your u on the right by a particular constant transformation, but you cannot multiply it on the left by that transformation and leave that invariant. In any event, we've got a geometry, we've got a bunch of u's, we've got our target space, or our reference state, our, there's a typo up there, sorry. We've got our target, and we've got our reference state, and so we can start finding geodesics, and in fact, you can solve this problem, but I'm going to simplify life for us a little bit in that the problem I described is a little bit too general for the physics problem. The physics problem actually had omega-1 and omega-2 equal to one another, and I'll also note that in the physics problem, defined as such, with this beta, it's actually a negative number. And so, let's see how that simplifies. Well, actually, what we're interested in is solving for a u that does this operation here. And so we just plug in our matrices. The subscript 1 now means at s equals 1, but we get an expression like this, and you compare. One of the things that you can see right away is that theta and tau always appear in that combination theta plus tau. And so that means that the difference isn't fixed in any way, but that was just this redundancy that I was talking about before. We're going to find a family of solutions, but then we'll be able to minimize the variables. If we compare here, if we compare here, these two are the same. That means, there's a difference in sign here. We better set the sign to 0, so you're tempted to set that equal to 0. But this is actually negative, and so a good way to do that is to make this actually pi rather than 0. And so that's what it says here. This sum is equal to pi. And so that's one boundary condition, and the y and the, well, you go like that. And so those are the boundary conditions of our problem. So here's a pictorial representation of our problem. I've suppressed y. Y is some extra direction, and the circuit just merely drifts along in that particular direction. The interesting geometry is in this tau, rho, and theta space. Again, rho is a radius in this space, theta is an angle, and tau is some linear direction. I'm supposed to start at the origin. That's u0, and then I'm supposed to end on this spiral where tau plus theta is equal to pi. So I can end anywhere on that spiral, and so I'm supposed to find the geodesics from the origin to the spiral, and it's some operation, and you can do that. But in words, what I'll say is if this was flat space, you would be able to figure out what the answer is right away. The shortest path from the origin to a point on the spiral is the one that just goes straight across along the pi, theta equals pi axis at tau equals 0. It's that green line. And sure enough, even though the geometry is more complicated, it turns out that that is actually the minimal geodesic. And our solution makes this particularly simple. The minimal solution, or the solution for the minimal geodesic takes that particularly simple form. means our circuit has this simple form. That's written in terms of boundary conditions in its coordinate space. You can evaluate the complexity, but what you'd like to do is translate it back to the parameters of the problem. And it turns out the cleverest thing to do is to write it in terms of the normal mode frequencies. And so there's some simple expression here involving the log of the two normal mode frequencies over a reference frequency that are describing the complexity of this particular ground state. And so I can do, well, you can do lots of things with that. But the natural question is, why does it look so simple in terms of the normal modes? Well, the normal mode space is just doing some rotation to our original x1 and x2. And so you can translate the problem and look at it from the perspective of the normal mode space. And one of the things you notice is that the reference state is still this same diagonal matrix. It's still a factorized Gaussian. But then, of course, the special thing is that the target state is also a factorized Gaussian. This is what we noticed back in the first lecture. There's no entanglement between these two modes. And so it's natural then that all our circuit does is it moves along and it pumps up these two normal modes, but it doesn't wander off in this basis into sort of introducing off-diagonal elements, because it would just have to reduce them to zero by the time it gets to the end. And so in this basis, then the circuit is, well, what I just said is just this simple diagonal circuit. And you can re-express that in terms of the original generators. But again, it takes some simple form with those two linear combinations, which are just then the x1, x2 representation of the generators in the normal mode. And perhaps, again, I'll pause and ask if there are any questions. If not, we carry on. Penalty factors. This is the idea that I may want to count different gates differently. And so in particular, you know, we've got a really simple problem here, but you might want to count the scaling gates differently than the entangling gates. One distinguishing feature is that those scaling gates act on a single site or a single oscillator, whereas the entangling gates act on two sites or two oscillators. And so when we think ahead to the N oscillator problem, you know, we think that locality is going to be important. And so in principle, I wrote down gates that couple sites that are arbitrarily far apart, but I want to penalize or give some heavy penalization to that. I don't think that is really kosher with the physics that we know about it, which we think is relevant. And so this is then, again, just a baby version of what happens when I introduce penalty factors. And so I'll replace my delta ij by something that weight, gives an extra weight to the entangling operators. Turns out that you get a far more complicated geometry, but at the end of the day, the minimal geodesic is unchanged. So this is in the top corner there, that's just to assure you that the geometry is more complicated. But then this is just saying that I get the same circuit, but because the delta ij got replaced, or I had a more different cost function, the complexity then of that minimal circuit or geodesic is different. And it's just that there's a factor of A that's associated with the off-diagonal components. I can try translating that to normal modes and the different ways to write the formula, but again, it has a simple expression, a relatively simple expression. And one of the things is it's just saying that in this problem, all you want to do is you want to pump up the different normal modes, but there's not really any advantage to wandering off into the rest of the space. And so that's why this trajectory is still the best trajectory in the problem. But let's think now about the real problem, which was a going to take a lattice in principle that's n by n by n by n, and d is again a space-time dimension, and so d minus 1 is my spatial dimension. But just to make a simple observation, I'm not going to do the real problem. I'm not going to worry about the entanglement. I'm just going to worry, I'm going to think that all I did was go from my reference state to one where the math got turned on, but in some sense the derivative terms did not get turned on. Then the complexity has a particularly simple form because all of the contributions to the sum are the same, and so I get a simple result like this. But there's actually a problem, quote unquote, or a feature of this particular result, in that n to that particular power is really the volume of my space over the cutoff to the corresponding power, but there's an extra factor of a half. And so I get something like v over delta to the power 1/2, whereas in the holographic problem, we saw things were extensive. We had v over delta to the d minus 1. That doesn't mean that this is wrong. It just means that this particular model doesn't reproduce a feature that we saw in the holographic case. But can we improve our model to sort of get closer to holography? Well, the answer is yeah. Let's just change the cost function. And one suggestion is, well, if we wanted a bigger power of n, let's just stick that extra factor of n into the cost function. But that's like saying that each gate, rather than counting a 1 for each gate, we're counting some factor here. And if we're throwing in an n, in principle, we could throw in some complicated extra geometric or curvature corrections as well to that factor. But that really seems problematic if we want to compare things with complexities when we change the volume or we change the cutoff. So I'm not in favor of this. Instead, I'd like to make another proposal, which is just starts with the question, where did that square root come from? Well, it came from our cost function. It came from that square root in the geodesic equation for action. So let's get rid of the square root. And so a better choice would be one where I just have a particular sum. So this is our original set of cost functions. I could use that. Or we might, have higher exponents. And any one of these cost functions will, it turns out, give me now a leading contribution in this particular problem where I'm now getting something that looks like holography, where there's a power of n to the d minus 1, or that volume over the cutoff to the d minus 1. So this is a better set of cost functions to think about if I want to compare to holography. So let's stick the omegas in there. If you believe me that the best thing to do is stay in what I call the normal mode subspace, then even in the lattice problem, although it looks much harder, I'll just get something that looks like this answer here, where there's some sum with logarithms of normal mode frequencies over our reference frequency. Of course, the dispersion relation in d minus 1 dimensions looks something like this. Yeah.
Regarding the normal mode subspace, since you're working on the diagonal and the matrix has square the number of entries in the diagonal, is it possible that the reason you're not getting the scale is just because you don't have enough that the off diagonal, just the number of entries in the off diagonal matrix, counting for the fact that you got square root. I'm not saying
You might think that, and if you carefully actually, there's lots of calculations that I just threw the answer up there, and there are factors of n wandering around. But with the right if you're careful about the normalization of the Fourier transforms and all of that, you don't get an extra n that way. Yeah, I'll just leave it at that. You can ask me more later if you want. We're almost at the end, and the bus is warming up. So I'll just say that, you know, one of the things about this problem is, as in any quantum field theory, stuff gets dominated by the UV. So the generic modes are all ones where some components of K, or K is roughly n over 2. And what that means is that, that's just where most of the phase space is out there. And what that means is that most of those normal mode frequencies are up near the cutoff scale. And so as a crude approximation to that sum, what I'm going to do is I'm just going to substitute omega as 1 over delta into the sum. And that gives me a particularly simple answer. But it's an answer that depends on this omega naught. And so at this point, I want to ask the question, what are we going to do with our reference frequency? One possibility is that we choose it to be some IR scale, or I've written it as 1 over a length scale, and that length scale is much, much bigger than the cutoff. And then I get an answer that looks like this, but that actually looks very much like the holographic answer if I choose that exponent alpha to be 1. In that I get my V over the cutoff, but then there's an extra logarithm that depends on the cutoff in this new scale. That was something we saw in complexity equals action. Alternatively, I might think a natural place to put the reference scale is up near the cutoff, and then the logarithm is just some numerical factor, and the leading order term in the complexity is just a volume over the cutoff, the appropriate power. That again is something with a certain set of choices we saw in complexity equals action or in the complexity equals volume case. And so let's compare to what I ended with last day. In the holographic case, when I was thinking about complexity equals action, I was stuck at a certain point because there was some arbitrary choice I had to make. And there were different choices that I could make for this new scale, which appeared in the normalization of the null vectors that define the surfaces. One choice was that I stick L to be the cutoff, which had some repercussions. It could be related to the volume, which had some repercussion, or undesirable perhaps effect. Or I could just pick some arbitrary scale, and it's a new scale that comes into complexity problems. Now if I compare to this side, I had this omega naught that would appear in my reference state. And I can make a same set of choices here, and in fact I get the same set of features appearing, and the complexity, this leading term, looks very much like what I'm seeing in the complexity equals volume. And so, you know, at the end of the lecture I said that this was something that we were left wringing our hands about, but here what the simple field theory model has taught us is that in fact I should have expected that, or that complexity is a different kind of a beast, and it just has this as a feature, that there's some ambiguity associated with the reference state, and it has various consequences for the numbers that come out of our calculations. So at this point I want to wrap it up. You know, that's a very simple model for complexity in a quantum field theory. Certainly there are lots of ways to extend it. But ultimately we'd like to understand how to connect this to holographic complexity. And I think really there what we need is a better idea. I think we're sort of, if I think about the entanglement entropy problem, I introduced entanglement entropy with this, you know, von Neumann formula, and I told you essentially what you have to do is take the reduced density matrix, calculate the eigenvalues, and then plug them into this formula, and that is the entanglement entropy. But then later in the lecture I said, well, there's actually a clever trick called the replica trick, and what we can do instead is we can manipulate the quantum field theory in ways that we're used to doing on the HepTH archive. And so, you know, there are some features that were unusual. There's a funny geometry in which we're evaluating a partition function, but it was really a physics approach to evaluating the entanglement entropy. Where I was at really with this simple model was I was saying, oh, complexity is the number of gates, so let's define some gates and look at some operations and optimize the circuit. And then I count up the number of gates, and that's the complexity. But what I really need is something over here. I really like some physicsy calculation, some manipulation, perhaps path integrals, partition functions. There's going to be some more familiar quantum field theory-like manipulation of the system, which gives us a number which, if it's not precisely this complexity, it might be some quantity that really reflects or behaves in the same way. And I think really it's only with that that we'll be able to make a clear connection to what's going on in holography, if what's going on in holography is we're calculating the complexity. And so there are some preliminary suggestions, actually, in particular, Tadashi's group or Takinagi's group have some interesting ideas in a paper in March, and there's a new paper coming out. And so if you're interested, I refer you to his talk next week in Tel Aviv. I know that he's going to be talking about some results that they've come up with recently. And with that, I will thank you for your attention, and I hope you enjoy the beach.